Hello everyone, I'm Giovanni Gabbolini and today I'm going to present you our work on the stability of embeddings for recommender systems in the case of matrix factorization. This is a joint work with Edoardo D'Amico, Cesare Bernardis and Paolo Cremonesi. Our work focuses on matrix factorization. This is a successful category of algorithms for providing users with recommendations selected from a catalog of items. Matrix factorization works by learning users and items embedding, which are represented in a common vector space. The dot product between embeddings measures the user-item affinity, allowing for recommendations. Embeddings are learned with a machine learning procedure that starts by initializing the embeddings at random. We are interested in evaluating the effect of the initialization in the final results, and in particular, if the effect is within a certain tolerance, we consider the algorithm to be stable and unstable otherwise. We believe it is important to investigate the stability issue. On one hand, the recommendation of an unstable algorithm might become unreliable. For example, let's imagine that an algorithm is trained on the same data, but with a different initialization. If it will provide different recommendations, will they be reliable? On the other hand, the stability might impact explainability. In fact, explanation for embedding-based algorithms are usually provided by identifying similarities in the embeddings. But if the embeddings are not stable, the quality of such explanation might be compromised. We carry out a preliminary study to investigate the stability of three common matrix factorization, namely BPR, Func, and probabilistic. We train the algorithms 10 times with different initialization, and we compare the recommendation at 10 using the Jacob index. That is, we train the exact same algorithm on the exact same data. The only thing that changes here is the embedding initialization. We do so in 5 common datasets. Here are the results. The algorithms show low values across all datasets consistently. On 3 datasets over 5, the values are bounded by 0.5. That is, the recommendation list overlap by less or equal than 50%. On book crossing especially, the behavior is particularly worrying. To investigate more deeply the instability, let us consider the anatomy of matrix factorization. It starts by initializing the embeddings at random, and then an iterative procedure begins. At every iteration, it samples an interaction made by a user with an item and updates the embedding of that user and of that item. Because of the well-known long-tail distribution of interactions, a large portion of both users and items embedding are updated few times. Such embeddings, that we call long-tail embeddings, will be more dependent from latent factor initialization, and we suspect that this might be one cause of instability. As we have just seen, matrix factorization treats users and items independently during the training. That is, at every iteration, it samples an interaction made by a user with an item and updates the embedding of that user and of that item. However, relationships exist between users and between items, such as similarity relationships. We introduce Nearest Neighbors Matrix Factorization for this reason. It leverages the similarity between users and between items while learning the embeddings. Nearest Neighbors Matrix Factorization also starts by initializing the embeddings random, and then it carries out the same iterative process. At every iteration, it samples an interaction made by a user with an item and updates the embedding of that user, of that item, and of their k-nearest neighbors. We say that the updates are propagated through the neighborhood, and this causes embeddings on the long tail to be updated more often, leading to less dependence from latent factor initialization and hence reducing the instability. Notice that the nearest neighbor matrix factorization generalizes matrix factorization. We return to the base form simply by setting the number of neighbors to 0. We repeat the stability of recommendation experiments, and here are the results. We notice a consistent improvement on all the datasets, with value doubled in a number of comparisons. The stability of our algorithm is lower than 50% in only one case. We also measure the stability of embeddings. Our intuition is that an embedding is stable if in every new latent space it is close to the same embeddings. To this extent, we compute the closest embeddings lists. Given a latent space and an embedding, we rank all the others based on proximity, and we do so for every embedding. As an example, consider a dummy two-dimensional space and 5 embeddings. If we were to compute the closest embedding lists, we would start by I1. The closest embedding will be I2, and then I5, I4, and so we start populating the list. Then we would also consider I2, and I3, and I4, and finally I5. The setup of the experiment is similar to the former. We train the algorithms 10 times with different initialization, and we consider the closest embedding lists of the replicas, and then we compute the Jacob index at 10. We use the cosine similarity as a measure of proximity for computing the closest embedding lists. Here are the results. We notice that matrix factorization struggles to reach a stability of 50% in many cases. Nearest neighbor matrix factorization, instead, show consistent improvement on all the datasets for both users and items embeddings, with values that fall under 50% in just 2 cases. Earlier, we have associated the cause of instability to long-tail embedding. Now we'd like to verify whether, in fact, a relationship between stability and latent popularity exists or not. For this reason, we investigate the stability of embeddings as a function of item popularity. First, we divide the bins in item in bins of popularity, from high popularity to low popularity, and we compute the stability of embeddings as done before, but now considering the bins. This figure shows the result of the experiment by running func on the last.fm dataset. On the x-axis, we have the bins. On the first bin, we find the most popular item that account for 34% of the total interaction, then 22nd, 26% on the second, 10% on the third, and so on. Notice that the first bin is also known as the short head. On the short head, we have equal stability of the two methods, while going on the tail, the stability of both algorithms decreases. However, we notice how nearest neighbor matrix factorization manages to mitigate the decrease in stability quite effectively. We have shown that nearest neighbor matrix factorization learns embeddings which are more stable, especially on the long tail. Now we turn to the performance on the long tail. We also compare our algorithm with competitive collaborative baseline, measuring the map at 10. And here are the results. We see that nearest neighbor matrix factorization managed to outperform matrix factorization in any comparison, except for just one. And nearest neighbor matrix factorization is the most performing algorithm in 3 datasets over 5. In the other 2 is the second most performing. The last analysis we carry out concerns convergence. We have seen that nearest neighbor matrix factorization updates more embedding than matrix factorization at each iteration. We are interested in investigating whether this translates to a lower number of epochs to convergence or not. For this analysis, we plot the training loss and map at 10 on the validation set. Here are the results for func on site you like. As expected, we observe a lower number of epochs to convergence. However, this comes to the cost of an higher time to complete every epoch. In conclusion, in this work we have provided, for the first time, evidence of instability of widely employed matrix factorization algorithms. We have introduced nearest neighbor matrix factorization, a generalization of matrix factorization that uses similarity during training. We have found that our proposal is more stable, more accurate on the long tail, and converges in a lower number of iterations. We think that our finding can have practical implications for the practitioners in the field that use recommendation and embeddings to several extents. Future works are addressed toward the study of stability of other embedding-based algorithms. Thank you very much for your attention.